Okay, all right, well, thank you, everyone, and thank you very much for the opportunity to be here. I see a lot of familiar and friendly faces in the audience, and that's very nice. Eventually, we'll get back to traveling again, and then I'll be very happy to come back to Pasadena in person. But in the meantime, it's very pleasant to get to do this remotely. Okay, so here's the talk. You guys can see my screen, right? Okay, so I should say that this talk is long. Cyprian said, please try to prepare a longer and more friendly talk. And I don't have to get through all of it. And I'm trying to be sort of friendly. But if I'm just talking into the Zoom screen for 80 minutes, I'll sort of go crazy. So please interrupt me all the time. And just whenever you have questions, just shout it out. I'm just kind of minimizing all the Zoom stuff so I won't see it. And we'll try to be enjoyable, do something fun. Okay, so I mean, the idea of this talk is kind of funny. Well, I don't know. So I call it Solid State Physicist Introduction. And what I really mean by that is not necessarily I'm assuming that you're a solid state physicist, but really I'm thinking the background that I would have needed personally to understand this stuff if someone had tried to explain it to me before I got involved. So my background is pretty far from quantum information in any sense, you know, aside from the fact that I took quantum mechanics, you know, in college. But I kind of had the idea of giving a talk that won't assume that you know anything about anything quantum information adjacent, and give you all the background that's needed. And I hope it works out. It's also very much not going to be like a review of the field in some larger sense. It's really going to be focused on the work that I was involved in specifically. So I'm not going to try to do anything comprehensive. I just kind of want to be friendly in the background. Okay, anyway, that's enough rambling. So this is work that I did with these three fellows. Adam and Jonathan and I were all postdocs at MIT at the same time, and we sort of fell into this work together. Stithvi joined us for the second part of this work that I'll tell you about. He was at Oxford, now is in Mumbai. Adam is now at ENS in Paris, and Jonathan's a professor at Bar-Ilan. Okay, so roughly speaking, I kind of want to tell you about two different works that are sort of encapsulated by these two papers. They're both quite long, I guess. This first one is about 20 pages, and this last one is a Leviathan at like 70 pages. But I'll try to just hit the highlights and give you the motivation and the key ideas. We don't have to get through all of it, and please stop me anytime. Okay, so I told you that I would try to, you know, not assume any knowledge. So this is a talk about quantum entanglement. And so the first thing I'm going to try to do is just to define what quantum entanglement is, maybe remind you what quantum entanglement is. So generally speaking, we say that something is quantum entangled when the state of the system cannot be specified describing all of its components independently. So you can't write the wave function as just a product of individual wave functions for each part. So, for standard examples, if you have two spins, an unentangled state of two spins would be one where the wave function just looks like a wave function for A times a wave function for B. And an entangled state would be something where it's not possible to write it this way. So standard examples, you have like a singlet state, and your wave function is a superposition of A being up and B being down, with A being down and B being up like this. So the problem with this definition, where you just say, you know, entanglement is when you can't, you know, write the wave function as a product of individual parts, is that it doesn't lend itself very well to asking how entangled is something, because this is kind of a binary question. Either you can write it this way or you can't. So in this talk, I'm going to take a slightly different perspective. And I'm going to say that quantum entanglement, say A and B are entangled whenever making measurements on B alters the set of A, alters the state of A, and in particular, it reduces the set of possible measurement outcomes. So in this product state, if I say measure the spin of B, spin B, then my wave function will collapse into something that looks like the wave function for A times just B being up, say. But importantly, after making the measurement on B, any subsequent measurements on A will be the same set of measurement outcomes as if I had measured A first. So whether I measure B first doesn't alter the set of possible measurement outcomes for A. The singlet state is obviously very different. So if I measure B first, then I collapse the wave function onto one of its two branches. And now any subsequent measurements on A will only yield down. So I've reduced the set of measurement outcomes from 50-50 either being up or down to definitely down. So that's, you know, that's kind of the workman-like perspective, or pragmatic perspective I'm going to take on what entanglement is. It's when making measurements on one part reduces the set of outcomes for the other part. The nice thing about this, about taking this perspective, is it lends itself very naturally to a question, to a way of asking or answering the question, how entangled are A and B? Because then you can say, well, by how much did I reduce the set of measurement outcomes for A by first measuring B? Okay, so the standard quantity for quantifying that is what's called the entanglement entropy. Sorry, I'm going to try to move something out of the way here. Okay, so the standard quantity is the entanglement entropy. So this is going to be the most mathematically technical slide, I think, in this talk, but it's not too bad. Let's just go through it. So if I have a system that's described by a wave function, then I can write a density matrix that looks like just this outer product of the wave function with itself. Now, I should say that throughout this talk, I'm only going to be thinking about pure states, by which I mean systems that can be described by a wave function rather than a statistical sum of different wave functions. So if I have a system that can be described by a wave function, I can write the density matrix. And let's just give a mechanical example here for a second. Suppose that my wave function looks like a superposition of up and down. So this is a single spin wave function. Say it looks like this. I can write it as a column vector like this. And then I can just take the density matrix. The density matrix is a 2x2 matrix, looks like this. So the nice thing about the density matrix is, to remind you, you can read off from the diagonal the probability of measuring different things. So 1/2 probability of measuring up, 1/2 probability of measuring down, and these off diagonal components sort of remind me that I have a quantum superposition of the two states. If it were just 0, if I just had sort of 1/2, 1/2, that would be something that describes like a statistical sum, like just a classical 50% probability of being up, classical probability being down, rather, and it's these off diagonal components that tell me that I have quantum superposition. Okay, let me just slightly more involved here. Is now I have two spins. This is the singlet state I was just telling you about, spins A and B. I have some single state like this. I can write my wave function as a vector like this. Now I have four components to it, corresponding to A and B being either up and down. I construct the density matrix by multiplying the wave function by itself, and I get something like this. Again, you can read off from the diagonal the probability of different measurement outcomes. So probability of measuring both up is 0, both down is 0, and then I have 50% these two outcomes. And again, they have a quantum superposition. Okay, so now in order to define the in order to find the entanglement entropy, what you want to know is, if I measure B, so in this case, B is just one spin. If I measure B, then by how much will I change the state of A? And the way you can do that is by first constructing the reduced density matrix. So this is a partial trace over B. What that means operationally is what it means is you're summing over possible measurement outcomes of B. So if I just imagine, summing over all possible measurements of B, what am I left with in terms of the state of A? So, okay, operationally, that means you take your density matrix, you divide it into different quadrants based on the state of A, you trace over each quadrant, and then in this case, you're left with something like that. Okay, so here's the reduced density matrix, row A, and what it looks like in this case is something that's just 1/2, 1/2. So that's something that looks like a classical superposition of 50% up and 50% down. It no longer looks like a quantum state like this that was in a quantum superposition of up and down. It looks like something that's just classically up and down. So if I sum over all possible measurement outcomes on B, I'm left with something that sort of has some statistical uncertainty to it. And particularly, it has some entropy associated with the state. So that's basically the idea. So the idea behind the entanglement entropy is take the partial trace over B, sum over all possible measurement outcomes of B, and then say the state that I'm left with, how much entropy does it have? This reduced density matrix that I'm left with, how much entropy does it have? If it's still in a pure state, then I have no entropy. So if A and B were unentangled, then when I trace over measurement outcomes of B, I'm left with the same state A as before I did that. And that state A, if it's a pure state, will have no entropy associated with it. It's just a pure state. It's in a very definite state rather than a statistical sum of different states. On the other hand, if they were highly entangled, then I'll be left with something that looks like a statistical sum of different states with lots of entropy. So now that's the idea. So what you do is you calculate the reduced density matrix by tracing out all the parts that are outside the subsystem you care about, subsystem A, And now you calculate the entropy that's remaining in that reduced density matrix. So it looks like trace of rho log rho. This should remind you of, say, sum of p log p, which is how you calculate the entropy of any, probability distribution. Okay, I went kind of fast on that, but any questions about this? This is just supposed to, give you a short starter course on the technical parts. But like I said, this is probably the part with the most equations, so it gets more friendly after this. Okay, all right, let's keep going then. Now, one sort of comment I'll make is that, in fact, there is like a whole family of different entropy functions that are indexed by this index n, and these are called the Renyi entropies. And they basically just correspond to taking the density matrix to different powers. So that's kind of like, raising the probabilities to different powers when you're doing the Shannon entropy. And then the usual one, which you call the von Neumann entropy, is just sort of the limit where this n goes to 1. Now, the nice thing, I'm not going to make a big deal about these different functions, because the nice thing is that for all n greater than 1, they're essentially the same. There's this nice theorem that says they're all bounded by, okay, so first of all, in the limit of n goes to infinity, you have a well-defined value. Basically, in the limit of n goes to infinity, the only thing that's left is the largest eigenvalue of the density matrix. That's the one that's, all the others are arbitrarily small compared to that large one. And so there's a well-defined sense of S infinity. And now S infinity provides both an upper bound and a lower bound for any other S of n when n is greater than 1. And basically what that means is that for n greater than 1, they kind of all have the same behavior. If one is diverging, then they'll all diverge. If one is a constant, then they'll all be a constant, and so forth. It doesn't make any claims about what happens when n is less than 1. So in general, what I'm going to focus on are basically the case of n greater than 1, and I'll sort of include n equals 1, so the limiting case of n equals 1 and above. And I'll talk about S0. So this is the limit where you raise the density matrix to the 0th power, and sort of all the elements on the diagonal are the same. They all become equal to 1 unless they were 0 to begin with. So it's sort of, you can think of this as taking the limit of n goes to 0. And then what you're left with is just some sort of counting number. You just count the number of non-zero eigenvalues of the density matrix. So the way you should think about this S0 is it's kind of a stupid quantity that's like a binary counting of, are two things entangled or not? So like if I take two spins and I don't apply any operation whatsoever that entangles them, then this S0 will be 0. But if I entangle them by any finite degree, like I have a Hamiltonian that couples them, but it's only acting for some infinitesimal time delta t, then this S0 will jump discontinuously from 0 to 1, or 0 to log 2. So in that sense, it's kind of a binary count of are two things entangled or not. And it'll be an especially useful thing for us to think about as a sort of a toy model. Okay, so that's the sort of technical background. But even if you didn't follow all the equations, the only thing you really need to remember is that entanglement entropy sort of is a quantitative measure of how entangled some subsystem is with its complement, and it corresponds roughly to the question of, if I make lots of measurements in A, by how much will I change the state of B? That's sort of the meaning of it. Okay, so what this talk is really about is thinking about quantum entanglement as a dynamical quantity and asking, how does it evolve with time? And this is something that has really picked up steam in the last, I don't know, 5 to 10 years. And a major tool for thinking about entanglement as a dynamical quantity is describing it using unitary quantum circuits. So I guess I don't know. I think people who are really into quantum information draw this picture sideways from the way I do. But in these pictures, I'll put time on the vertical axis and position on the horizontal axis. You can think of this as an array of spins or qubits. And now the idea is that I'm describing the time evolution by a sequence of discrete operations. So each of these green boxes corresponds to some operation that is now, some unitary operator that's applied to the two spins that it's connecting. So in general, this operation will create some entanglement between two spins. And now I'm going to describe my time evolution by as a discrete sequence of such events. So you could have it, if I just was randomly doing operations, if I looked like one on the left, but you can also imagine some ordered process, maybe like this. And it's some picture like the one on the right is commonly used to approximate continuous time dynamics. So in the limit where you have very many of these operations and each one is very weak, somehow close to the identity, you can use this to describe or to approximate continuous time dynamics, so some continuous time Hamiltonian. Okay, but in this talk, what I'm mostly going to focus on is random dynamics in some sense. So either the operators themselves being random or their placement in time and space being random. Okay, so before I start talking at all about our work, I want to tell you what got me into this business, or what got me first excited about it, and what I view as sort of a seminal and especially exciting result that provided a way to think about the statistical mechanics of quantum entanglement growth. So that's this PRX paper. It sort of happened down the hall from me when I was a postdoc. So the idea was to just think of entanglement dynamics as a kind of a surface growth problem, like so imagine that you had a array of spins or qubits, and now you have some procedure by which you randomly apply unitary operations in time and space. And then I asked you, well, how much entanglement is there at some time? Well, the first thing you should notice is that in order to ask the question how much entanglement there is, I have to define a subsystem. I have to say how much entanglement is there between A and B, and I have to define what A and B are. So if you ask the question, for example, how much entanglement is there between the left and the right, then that depends on where I define left and right. So I have to introduce a partition that divides the system into two sides. And if I move the partition, then the answer to that question will change in general. So the idea of this paper was, let's think about the curve entanglement as a function of position and time. So this position now means position of the partition. So it means entanglement between left and right, with left defined as everything to the left of X. And in general, that will trace out some curve at a particular time. And it should vanish at the ends, because at the ends your subsystem becomes empty. And then it looks like some kind of curve. And the very clever thing that this paper did was to say, well, let's imagine the time evolution of this curve, which will generally be growing in time as I apply more operations and the more entanglement is created in my system. And you can think about the dynamics of this curve as something like a random surface growth problem. Okay, so here is, I think, how I see the cleverest thing in that paper. So I said, okay, imagine some time t, you have this curve S of X. And now let's suppose at that instant in time, I apply an additional unitary operator at some point. So that will generally make the entanglement at that point grow. So, if my partition is such that all of this corresponds to the left, then doing something deep inside the left side doesn't really do anything. But if my partition is defined so that it cuts right through this unitary operator, then applying that unitary operator will produce a little bit more entanglement in general. So it will, if my subsystems are defined like this, then applying this operator will produce more entanglement between left and the right. Okay, so generally speaking, I apply that operator and this curve goes up a little bit at that point. Now, one thing that you can notice is that at a given moment in time, as I sweep the position X, the entanglement cannot change by more than 1 unit if I shift X by 1. So what I mean by that is, say, this point and this point can't be different by more than log 2. And the reason for that is just that, like, when I move the point X to the side, all I'm really doing is shifting 1 spin from A to B. And 1 spin can only have 1 bit of information. So I cannot change the entanglement by more than 1 unit between X and X plus 1 or X minus 1. So now the clever thing that this paper did was to say, well, let's imagine now that the entanglement is growing by the maximal amount consistent with that constraint. So in other words, let's suppose I have some curve, and then I come and I apply an operator at some particular point. It's going to make the entanglement grow. And let me imagine that it immediately grows to the maximum amount that's allowed by the constraint that S of X cannot change by more than 1 unit between X and X plus 1. So then it becomes a kind of a classical surface growth game where you have some kind of random surface, and then you pick a position in space randomly, and then you say, oh, I'm going to grow the entanglement by as much as possible. And say, in this point, that means it can grow by 2. If it grows by 2, then it's only separated by 1 from each of its neighbors. If I had picked this point, it would not be able to grow, because if it grew at all, it would be 2 different from the one on the right, and so forth. And you can sort of go by. So you can imagine this process of random surface growth. And this becomes a sort of an upper bound on the entanglement at every moment, because you're imagining that the entanglement is growing by the maximum amount allowed at every time. And then you can describe the classical statistical mechanics of this surface growth. And that's what they did. And they were also able to prove that this amount is an exact description of this S naught, which I told you was sort of this binary counting variable that sort of tells you, is there that for 2 spins just says, are they entangled by any degree or not? And this sort of classical game it turns out to be an exact description for S naught. And they were able to show that.
Can I ask a quick question?
Yeah, please.
Just wondering if, is it inevitable that this gate should increase the entanglement?
Yeah, sorry. This is a good question. And I guess I didn't say this. That I'm assuming that these gates are sort of randomly chosen. They're chosen randomly from the space of all possible unitary operations. And in that case, it does sort of become inevitable that the entanglement is always going to increase. It's not true. If you could choose some subspecial operation, you could sometimes decrease the entanglement. But in the limit, if you're always choosing a completely random one, then that becomes a set of measure 0 in terms of probability, likelihood for that to happen.
Okay, thank you.
Yeah, sorry, I didn't say that clearly. This is really a description of random unitary operations. Okay, so then, by this classical surface growth problem, they were able to show it's described by what's called the KPZ equation, which is sort of a generic description for random surface growth. And the KPZ equation is kind of nice. It pops up all over the place when you have some random surface growth problem. I first heard about it in the context of you take a piece of paper and you light one end on fire, and then there's a burning front, and the movement of that burning front is described by the KPZ equation. So in terms of this entanglement growth problem, where you're applying random unitary operators sort of randomly in space, you have this curve. Entanglement is a function of position and time. And there's a family of these curves at different time, and they look like this. So here's what you're seeing. So here's some early time. Now what you're seeing, this slope on the left side, is the entanglement becoming completely saturated to the maximum amount that's allowed by the constraint. And then over here, it's not completely saturated, it can continue growing, and you sort of get random fluctuations. And as time progresses, the region of space that has a completely saturated entanglement is now growing larger, and these fluctuations are sort of getting bigger. And the nice thing is, by mapping to the KPZ equation, you can immediately say whatever you want about the critical exponents of these fluctuations. So for example, you can say that there's a correlation length of fluctuations of the entanglement as a function of X that grow like T to the 2/3, and the amplitude grows like T to the 1/3, and so forth. And the nice thing is that once you've made the mapping to the KPZ equation, you can sort of look up all of the many stat mech problems that KPZ describes, and then you can find out famous results from those fields and then port intuition from them. So for example, KPZ describes the problem of directed polymers, like trying to lay a polymer through some disordered landscape in space and talking about its fluctuations. And some very important intuition came from thinking about polymers and then making the mapping back to the entanglement problem. Okay, so there's this beautiful family of curves that I told you about. And that comes by imagining that you're moving the partition X in space. But for most of this talk, I'm just going to fix that X to be right in the middle of the system. So I'm going to talk about the left side and the right side. And I will define that so the two halves are equal. I can call it the bipartite entanglement. And if you do that, then what you'll see is the entanglement grows, generally speaking, linearly in time. So this sort of front is moving up and up with time. And it has sublinear fluctuations that are like t to the 1/3, as I just mentioned. But mostly what you just need to know, if I fix that position, is that the entanglement is growing linearly in time. And then finally, at very, very late times, then this sort of pyramid will finish growing and it'll just come to a point, and the value of that thing will saturate, and it'll saturate at something proportional to the system size. So this is what you call volume law entanglement. The idea is that the entanglement between left and right is proportional to the total number of spins in your system. You've saturated something that's proportional to the system size. So, this is commonly described in the language of scrambling of information. Like your initial state had one bit of information per spin, and initially all that information was localized, right at the position of each spin. And as time progressed, each bit of information sort of got scrambled over its immediate neighbors. And then after a very long time, every bit of information is completely encoded, equally on the left and the right. Okay, so this picture, from my vantage point, it really kicked off a lot of work on the statistical mechanics of entanglement growth using this random unitary circuit description. And I'm not really going to do any justice to the wide set of very interesting work that's come out of it. So, for example, describing the same picture in this same business in the Heisenberg picture, where you have spreading of operators over time. We're talking about out of time order correlators. How does this picture modify when your dynamics has conserved quantities in it? That's sort of outside what I just told you before, where you're picking completely random operators every time, and this sort of relates to Jason's question. And then you can talk about not just what happens to the entanglement entropy, which is sort of a global quantity, but you can talk about sort of what happens to some kind of level statistics as your time goes on. Anyway, I'm not going to go into that. The only thing you really need to remember from this early part of the talk is that unitary evolution generically leads to linear in time growth of the entanglement entropy, and after a long time, something that's like volume law entangled. Okay, so now I'm finally ready to tell you what's the question that we're actually interested in. And the question we got interested in is what happens when you have a quantum system that's undergoing both unitary evolution and sporadic measurement. So in addition to some unitary operations that are trying to grow the entanglement, someone is coming along and grabbing a random spin at a given time and measuring its Z component. And when you do those measurements, you tend to reduce the entanglement, basically just by taking one spin and you've given it a definite value, you've written it down. And now that spin cannot contribute to anyone's entanglement anymore. And generically speaking, the entanglement should go down. So the question is, how do these two factors compete with each other when you have random unitary operators trying to make the entanglement grow, and you have measurements trying to make it shrink? In a sense, you can imagine what's happening without the measurements is that the wave function, which originally had a specific value, is sort of growing to fill the whole Hilbert space. But every time you make a measurement, you collapse the wave function, and it reduces the volume of Hilbert space that it occupies. Okay, so the big question that we're after is, if you have these two things simultaneously, then what happens? Does the entanglement continue to grow linearly in time and saturate some volume law value, or does the measurement halt the growth, leading to area law entanglement or something that doesn't grow in time with anymore? So it turns out that there were a couple of groups that were interested in this question simultaneously. And in the very early days, we had some disagreement about what you should expect. And it seemed like there was a pretty simple argument that any finite rate of measurements should give you area law entanglement, that any finite rate of measurement would halt the growth of entanglement. And the argument sort of goes like this. So imagine you start from some product state, say they're all spin up. And then as the dynamics continues, you can imagine that spins first get entangled with their nearest neighbors and then the next nearest neighbors. And there's sort of a growing length scale in time. And that sort of length scale, almost like a light cone of entanglement growth, grows linearly with time. And you can basically think that those spins that are within that length scale of the midpoint of the midplane are contributing to the entanglement. So that's a sort of a heuristic picture for why you get a linear time in entanglement growth. So you can say that if you talk about the entanglement between left and right, it grows ds dt as some constant. Okay, so now if you have measurements, what you can think is that perhaps at a given time t, you measure some fraction of the spins that are within that length scale. So now by virtue of measuring them, they're not contributing to the entanglement anymore. So you can sort of surmise, I suppose, that maybe you have ds dt, it has this constant term in it, but also has a minus p times L term, where L is this length scale. And since L is proportional to S, you get ds dt is constant minus p times S. Oh, sorry, p is measurements sort of are acting against the entanglement growth. And you can say, well, at long time, let me just look for solutions where ds dt is 0. And what you'll find is that in the limit of infinite time, ds dt becomes 1 over p. So it becomes something that's independent of the system size. So this was sort of the argument. And what it would tell you is that you get area law entanglement, something that doesn't depend on the system size, for any finite measurement rate. And it's just the value of that area law coefficient goes like 1 over p. So this was one of the two. This was a possible argument that was advanced. And I want to try to convince you that this argument is wrong, and that it's sort of a failure of geometric imagination, I suppose. And instead, the result that I want to sort of explain to you is that there's a specific measurement, a specific critical measurement rate that separates a volume law phase from an area law phase. So specifically, when a measurement rate is smaller than some critical value, you get an entanglement that grows linearly in time and ultimately saturates something according to the system size. And when the entanglement is bigger than the critical, when the measurement is bigger than the critical rate, you'll get something that saturates to a finite value, even in the limit of infinite system size. And separating them is a critical measurement rate at which the entanglement grows logarithmically in time. So this is a phase transition. It's now a sort of phase transition in the dynamics. And that's what this talk is about. Okay, so that was the long background. I hope you're still with me. And now I'm going to sort of describe to you these two works. First, I'll talk about 1 plus 1D case, or sort of the pictures I've been drawing so far of a one-dimensional chain of spins with nearest neighbor coupling. And then I'll tell you about our attempts to sort of figure out something more generically in all-to-all coupled systems. Okay, questions at this point? I mean, now is a good time to raise objections.
I have no objection, but I did have a question.
Sure.
Maybe you'll get to this later, but is there a way to think about some correction to the KPZ equation that kind of represents the introduction of measurement?
Good question. The answer is I don't know. Sorry. This KPZ thing I thought is very pretty, and I couldn't help telling you about it. But I'm sort of going to neglect it for the rest of the talk. So in terms of the entanglement growth, you have a linear T part, and then the KPZ tells you what the sublinear behavior is. For the rest of the talk, I'm sort of going to neglect that completely because we were sort of focused on a more basic question.
Okay. Thanks.
But I don't know that that's known, to be honest. Okay, other questions? All right, then if not, let's bravely push on. Let me minimize the Zoom stuff again. Okay. All right, so now let me focus on the question of the 1 plus 1D system, which I imagine a 1D chain of qubits or spins. And now they're going to undergo a protocol in which I have, these unitary operators applied between nearest neighbor pairs, also with some finite rate of measurements. So this has been branded the hybrid quantum circuit or something like that. Hybrid, I guess, because you have measurements plus unitary dynamics. So I imagine starting from some product state at time 0, and then I have unitary operations, and each of these black dots represents the possible location of a measurement. So for each black dot, I roll a dice, and if the probability, with probability P, I make up a measurement. And by measurement, I really mean like you take the wave function and you evaluate by the Born rule what's the probability of measuring up versus down is, and then you pick one of those two branches with the corresponding probability, project the wave function onto that branch, and continue the evolution. So it's very important that we're not averaging over measurement outcomes, which would basically lead to decoherence. We're always following a pure state. Okay, so we follow this protocol and we calculate the entanglement entropy as a function of time. Just a reminder, that's how this thing is defined. Oh, sorry, this is some typo. Sorry, this should be trace of, anyway, it doesn't matter. Right, okay. And then we what you can do is just do numerics. You do an exact simulation of this. We used I-tensor matrix product representation. Okay, so obviously the result I'm going to tell you about is that you have this phase transition in the dynamics at a critical measurement rate. But in order to understand where that comes from, or sort of how we anticipated it, I think I need to introduce you to the concept of what we call the minimal cut. And the concept, this is something very useful that comes from the polymer analogy. And you can think about it like this. Imagine if I had started with a pure state. Imagine if I had started with a product state like this. And then for whatever reason, the series of operations that I applied look like so. So lots of operations, but you'll notice that there are none right at the midpoint. And then I asked you, what is the entanglement between the left side and the right side at the final time? Well, it's kind of obvious that there should be no entanglement. Like at the final time, these are just two independent systems. Each one is very entangled, within itself, but there's no entanglement between left and right. So if you want, you could draw like a red line that separates the left and the right. And you say that red line separates two causally disconnected pieces that can't be entangled with each other. Okay, let's go to a slightly more complicated example. Imagine if I had this sequence. So now these circles with arrows in them correspond to positions and locations of a measurement and the measurement outcome. Okay, so let's say, so first time step, okay, so here are spins. First time step, I apply unitary operators that tend to entangle neighboring spins. But then immediately after the first time step, I measure spin 4. Let's call this guy spin 4. I measure spin 4. So spin 4 was briefly entangled with 3, but after measurement, it's entangled with no one. Okay, so now next time step, I take this operation and I entangle 4 with 5, but then I immediately measure 4 again. So what you'll notice is that after this time step, nothing on the left is entangled with anything on the right. Stuff on the right got briefly entangled with 4, but then 4 was measured again, and it's not entangled with anyone. So the point is, I guess, that by this process of repeatedly measuring spin 4 over and over and over again, I prevent any entanglement from forming between the stuff to the right of 4 and the stuff to the left of 4. So at the final time, where 4 has a definite value and nothing on the right has been entangled with anything on the left, I can say that there is no entanglement between the left and the right. So if I did this protocol, and then you asked me how much entanglement is there between the left and the right at the final time, I would say there's none, because I kept measuring this one over and over again, and it sort of blocked any entanglement from forming. So now I can draw my red line, and it separates left from right causally, and it gets to sort of pass through the locations of measurements. Okay, last example, suppose I have something like this. There's some initial dynamics that entangles everybody with everybody, and then at some time, I measure everyone on the left, so they're back to being a product state. And then I do this business again of sort of measuring the one at the midpoint and preventing any entanglement from forming between left and right. And so now I can sort of, again, draw this red line. And you say, as long as I wrote down the outcomes of all these measurements, nothing inside this red line can have any entanglement with anything outside. So at the final time, this stuff on the left and this stuff on the right, there's no entanglement between them. Okay, a sort of interesting question set becomes, well, what would happen if I didn't make this measurement? So I just remove one of these measurements. Now I can't claim that left and the right are absolutely causally disconnected. But what I can say is that their only entanglement can come from the value of this one spin at one time. And you can convince yourself that that one spin at one time can convey at most one bit of information. So in this case, the entanglement between left and right is bounded by log 2, cannot be more than log 2. Okay, so now you're ready for the general formulation of this idea of the minimal cut. And the idea is to basically draw your circuit and imagine it as like a geometric object. But wherever there was a measurement in your circuit, think of it as like a broken link. And then ask yourself, is it possible to causally separate the left side at the final time from the right side at the final time? Like just imagine grabbing these 3 with your left hand and grabbing these 3 with the right hand and trying to pull them apart. And if they come apart, without any resistance, then that means that they can't have any entanglement with each other. And if they don't come apart, then you can ask, well, how many legs of the circuit would I have to cut in order for them to come apart? So you can imagine cutting up your circuit in many different ways, but one of those ways corresponds to the minimal number of cuts that you need to make. And if you find what is that minimal number of cuts that I need to make, that will give you a bound on the entanglement between the left and the right at the final time. And that idea is called the final cut. It's sort of an equivalent of, in general in networks, you have this idea of the min cut max flow theorem. But okay, anyway, this is the minimal cut. And it turns out that this minimal cut is exactly what I called S naught. So that this zeroth Renyi entropy. Okay, so the nice thing about it, this sort of geometric problem of cutting up your circuit, it becomes exactly a problem of first passage percolation. Actually, as far as I know, this is why the whole field is called percolation, because people were imagining like water is dripping down from above through some porous medium, like when you're making coffee. And then you can ask, can the water go from the top to the bottom? And if it can't, how many passages would you have to unblock for it to do so? So that famous percolation problem becomes an exact analog, or it becomes exactly mappable onto this question of what is this bound S naught on the entanglement? So, okay, so here's the circuit, and it maps exactly onto a problem of first passage percolation. And one of the very clever things done in this early paper that I mentioned was to show that this minimal cut gives you this exact bound, and that the bound is in fact saturated in a certain, I guess, kind of unphysical limit, where each spin is spin q and q goes to infinity. So you can think that the local Hilbert space of each qubit, I guess I shouldn't say qubit anymore, but the local Hilbert space of each site goes to infinity. And in that limit, this entanglement bound gets saturated. Okay, so this is actually where I first got excited about this business. So Jonathan and Adam, and this is Chongwon Ha and Sagar Vijay, they were doing this down the hall, and I thought it was very cool. And then we were talking about it over lunch, and when it became clear that there was a possible analog of percolation, that's when I got excited and started maybe being useful, because it reminded me of this problem that I had learned as a freshman in college. My first physics teacher in college was a guy named Dick Zallen, who had a long career at Xerox doing semiconductor stuff, and he taught me this famous percolation problem, which he called the Vandalized resistor grid. And the idea is that you imagine like a big square grid of 1 ohm resistors, and then you apply a 1 volt battery between the left side and the right side, and you ask how much current flows. And okay, if in its natural unbroken state, this grid has an effective resistance of 1 ohm and carries 1 amp of current. But now the idea was to imagine that you have some vandal, this guy, who comes through and starts randomly cutting links in your resistor grid. And each one of them goes from resistance 1 to resistance infinity, current can't flow. And at some critical fraction of cut links, the circuit will just fall apart into disconnected pieces, and there's no path between left and right. And at that critical point, the current vanishes. And then you can sort of study what's the critical behavior of the current as it approaches, as you cut more and more links. And turns out to be a critical fraction. It's 1/2, and the limit of a very large system size. At 1/2 fraction, you disconnect to the left and the right. And then there's a critical vanishing of the current with an exponent that was known. Anyway, I thought this problem was very cool when I was a freshman in college, and I was excited to get to use it again. So how does the mapping work in this problem? So this is in the minimal cut problem, what I'm looking for is a pathway that can go from the top of the system to the bottom, and that will separate the left and the right side. And I'm looking for the minimal pathway. If I have no broken links in my network, then that pathway necessarily has to pass through like every vertical layer, and it makes 1 cut per size in the vertical direction. So that minimal cut has a cost that's proportional to the vertical direction, which in this case is time. And consequently, my bound on entanglement S, I guess I should say S naught, is proportional to the time. So this is sort of an entanglement that grows linearly in time, which is what I was telling you about at the beginning. Okay, so what happens when I make lots of measurements? And now measurements are kind of like pre-broken links in this network. Now, I was taught by my PhD advisor, Shklovsky, to think about percolation like a network, a percolating network, as something like a ripped up net. Like you have a fishing net, and then fish have broken lots of pieces in it. And this ripped up net has a characteristic like hole size that's given by the correlation length psi. So psi has some dependence on in this case the measurement rate p, which is like the number of cut links. And when I draw this net, when there are lots of things that I'm not drawing, which are like little places where some piece of the net has just fallen off, or lots of dangling loose ends. But I can just draw instead something that looks like the backbone of this net. And that's what has this correlation length. Anyway, so now if you ask the question of, if I want to make a cut that crosses the vertical length of the system and separates left and the right, and how many cuts do I have to make? I have to make one per length psi. So I gotta make one set here and here and here and here. So I make one cut per length psi. And since the vertical size of this thing is t, then you say the entanglement looks like t over psi. So that's t, still growing linearly in t, but with a rate that is renormalized down, and that has this critical vanishing as I approach the percolation threshold. Okay, so now you can ask, well, what happens when I approach exactly the percolation threshold? And at that point, this length psi grows to be of order the system size. And now you don't have any characteristic length scale in your system. Instead, you have like a hierarchy of different length scales. So the way that we imagine it, at least, is to imagine that you have like empty chambers. So you're trying to draw a minimal cut that goes from the top to the bottom. And it can sort of, generically it starts in some void of size order 1. And then you can, by judicious choice of cut, you can go into a void of size order 2, and there to order 4, and there to order 8, and so forth. There's sort of a fractal landscape in which you have every length scale present. And so by choosing your cut appropriately, you can go from one length scale to the next one up, to the next one up, and so forth. Anyway, I'm saying this poorly, but I'm basically trying to motivate a known result in the first passage percolation, which is that this number of cuts grows logarithmically with the system size. You have to make one cut per length scale. Okay, so finally, what happens when you're above the percolation threshold, when you've made so many cuts that now your network has fallen apart into many disconnected pieces? The largest pieces have a characteristic size, psi. And generically, you're going to say start in something like this, and you have to cut your way out of that initial cluster, and then you're free to pass all the way through. So another way to say it is that the only thing holding together the left side and the right side at the initial time is some cluster size psi, and that has a particular size, and you have to make log psi cuts to get out of that initial length, that initial cluster, and then you're free and you've separated the two. Okay, so putting it all together, what do we have? We have something that there's this sort of percolation type bound on the entanglement, and it has 3 regimes of behavior. When the measurement rate is smaller than some critical value, you get entanglement that grows linearly in t, and that vanishes critically at a critical value. When you're exactly at the critical rate, you get something that grows logarithmically in time, and when you're above the critical rate, you have something that no longer grows with time, and it's just some constant. It may depend on p, but does not depend on the system size anymore. So that's sort of the result I was trying to tell you before, that you have now 3 regimes of behavior with a critical measurement rate separating them. Well, I guess you have two regimes and a critical measurement rate separating them. Okay, questions at this part? This is maybe.
Are you going to tell us directly the flaw in the previous argument that you?
Oh yeah, I mean the flaw in the previous argument, I guess, was, okay, how do I say this? The flaw in the previous argument was, I suppose, just imagining that you have a single variable that's like a length scale, and when you measure, you contract the length scale structure that's growing in time, and you can make holes in it, but that's a different question than whether the structure is still growing. I guess it's sort of I don't know how to say this. Sorry. Let me go back. Oops. Sorry, I stopped sharing. I didn't mean to do that. The basic problem, I suppose, was imagining that there's like one variable. I guess it's kind of like you can think of it as like a failure of mean field thinking. That like you imagine that there's like one variable s that has a mean field growth rate, when in fact there's sort of this spatial structure, and you have to think about it in a percolative way. I don't know, that's probably not as maybe. Okay, let's see, where was I? Okay, I was here. Sorry, other questions? Okay, well, if not, let's.
How does the size of the infinite cluster scale when you have P less than PC?
Yeah, I mean, well, okay. Maybe what you mean is like the mass of the infinite cluster, like the total weight of everything connected to the infinite cluster.
Right.
Yeah, that has some, that has some other critical exponent. So I sort of mentioned the critical exponent describes the correlation length, but there's a different correlation length, a different critical exponent that describes the sort of total weight of the infinite cluster. It turns out to be not so important for the minimal cut problem, basically because so much of the weight is taken up by these sort of dangling ends, which are not relevant for the minimal cut problem. Anyway, some other correlation, some other exponent whose value I don't remember.
I see. Yeah, I'm just asking because if you look at the bond percolation problem over there, like the size of the largest cluster, like the linear size of the largest cluster, it will scale, it will go like L to the 1.1 or something. Like it doesn't scale with L, it doesn't grow linearly with L. So
yeah,
the smallest path you have to take to go from one side to the other side,
right.
That scales like L to the 1.1.
Yeah, sorry. So I think you're thinking about, like, say if I have this point and this point, and I ask how long is the line connecting these 2 points, and it doesn't scale like psi, it scales like some other power of psi.
Yeah.
Is that what you're thinking?
Yeah.
So for one thing, I think that's only true in 3D, and in 2D, like that 1.1 is a 3D result, and in 2D it's still just 1. But again, it's also not that relevant for the minimal cut problem, which is just asking me to, like, how many cuts do I have to make? And the sort of tortuous length of this segment doesn't matter, because once I cut through it, I'm through.
Okay, thanks.
Okay, all right. So here we are. Okay, a nice tool that we can use is if you have these 3 regimes of behavior, you can capture them all with a single scaling function. So generically, when you have critical behavior, you should be able to write all your properties in terms of system size divided by the correlation length. So the correlation length has this 1 over P minus PC to the new behavior, and you can equivalently write it as something that looks like this. So you can think of this as basically system size over correlation length. And now you can imagine 2 different protocols. You can either imagine finite time and taking system size to infinity, and this is basically thinking about the time, the growth in time, or you can imagine finite system size and then take the limit t goes to infinity, and then ask, in the final saturated state, how does the entanglement grow with system size, volume law, or area law? Okay, so now let me show you results for S naught. So this is, like I said, we do exact simulations of the quantum dynamics, and then we take this 0th Renyi entropy, which basically just comes down to counting the non-zero eigenvalues. And what you're seeing here is S naught is a function of time for different measurement rates. So this P equals 0, there's no measurements, you get entanglement growing linearly with time. And what you're seeing is that for higher measurement rates, you still get a linear growth. So this is a log-log plot. So everything with the same slope is linear growth, and different vertical offset means different coefficients of linear growth. And then when the measurement rate becomes bigger than some critical value, you see that it doesn't grow with time anymore. It saturates to a constant. And the value of that constant can depend on the measurement rate. And then, okay, here's exactly the critical value. And then you can say that, I guess that's a log, but it's hard to really demonstrate a log, I guess. Okay, so here's the growth rate. So the growth rate of S naught as a function of the measurement rate P, and you're finding something that sort of vanishes critically at a particular measurement rate. And this is exactly like this vandalized resistor grid problem I was telling you about, that this vanishing of the growth rate is an exact analog of the vanishing of the current. And in fact, there's no fitting to this red line. You just look up the percolation, the percolation threshold and the critical exponent that are known from classical Newton percolation. Okay, so now let me just show that we can do critical scaling. So here is, now this is the limit of infinite time, and I'm showing the entanglement at different system sizes for a given P. Sorry, entanglement is a function of P for given system sizes. And what you're seeing here is that when P is large, the entanglement entry does not depend on the system size. So this is what you call area law. But when P is small, the entanglement grows linearly with the system size, and this is what you call volume law. And now you can do critical scaling, put all these curves on top of each other, And there are no free parameters here. We're just using exactly the values known for classical percolation. Okay, so I sort of mentioned that I was going to talk sort of about two cases for the Renyi entropy, what I call the zeroth Renyi entropy, and then there's like the generic case, which is, you know, n1 plus. So here's the von Neumann entropy, and I should say that this zeroth Renyi entropy is an upper bound, but it doesn't have to exactly describe the real transition. So it could be that everything is area law, and all we have is an upper bound, and we can prove that that upper bound has a transition. So really, the situation we were in is to sort of say, well, we know this upper bound has a transition. We can write down all its properties. Let's just use that as motivation to check whether the real transition, so the generic transition also, sorry, the generic entanglement entropy also has a transition. So then we do our numerics, and this is what you see. So you're seeing at large P, the entanglement doesn't depend on system size after a long time, and at small p it does, it grows linearly with system size. So it looks like there's a real transition, and then you could look for critical scaling. Now we don't know a priori what are the critical properties. We don't know what should be the critical measurement rate, nor what should be the critical exponent. But we can just sort of look for scaling collapse and search in this 2-parameter space, and you can get a very good collapse. And it really looks like there is an entanglement transition. And then, okay, this is our best estimate from the scaling collapse, but my understanding is that these two values still have no theoretical derivation. So here's the situation. You know, this is the situation as we first presented it, that it looks very much like there is a transition between an entangling state and a disentangling state. Entangling meaning the entanglement entropy grows linear with time, saturates something with volume law. Disentangling meaning it doesn't. And there's some critical measurement rate, PC, whose value we don't know how to derive. But we sort of motivated our scaling behavior and our expectation that there should be a transition by thinking about classical percolation. But classical percolation does not give you the right measurement rate. So that's, I guess the way to think about it is that there's a low measurement rate where you get entangling dynamics, and then there's a very high measurement rate where you get non-entangling dynamics for a kind of trivial reason, which is just your circuit falls apart into disconnected pieces. And then there's kind of this no man's land in between, where geometrically your circuit still admits, you know, connectivity, but that connectivity is somehow too tenuous, and you get area law, and you don't get entangling dynamics. You get entanglement that saturates to some small value as a function of time. So this is the picture as we presented it. As I mentioned, it was sort of, there was some disagreement about it, but I think by now this picture has pretty broad consensus, and people looking at it in different ways. And it's really sort of sparked a lot of research and a lot of people trying to figure out what are the properties of this true transition. We can only really write down the properties of the classical transition. So what is this one? Okay, so that's kind of the end of part one, and I'll do the part two I'll do much quicker, which is just to sort of give you some information, give you some idea about how we went about trying to find some exact solution for this true transition. But maybe now is another good point to pause and ask for questions, or even let people, you know, stretch out and relax for a second.
Yeah, I had a question, Brian.
Yeah.
So as you emphasized, it's important that you're post-selecting on these measurement outcomes. If you averaged over them, then you'd be decohering the system, and there'd be entropy, which wasn't entanglement entropy, essentially getting pumped in by averaging over those measurement outcomes.
Right.
But suppose that rather than doing projective measurements, I consider some decoherence process that, like amplitude damping, you know, where ones decay to zeros and not the other way around. Like suppose it's atoms, and the excited states can decay to the ground states. So that would be a way of, you got to have some way, if you're going to get the entanglement, you have to you know, be able to withdraw entropy. But it seems in that case you would still have a competition, right, between this loss process and the generation of entanglement. So there could still be an interesting transition.
Yeah, that's okay. I see. So I think what you're saying is, let me replace each of my measurements with something that looks like a finite probability of just going to the zero state.
Yeah, which would actually happen, right? If I had a bunch of atoms in excited states or ground states.
Yeah, actually, that's an interesting way to think about it. And you're right that generically there would also be some competition there. It's a little confusing because either in the limit where the measurements are absent or in the limit where the measurements are, sorry, these sort of,
Yeah.
I don't know what you want to call these processes, or you had some language for it that I've already forgotten. In either extreme case, I end up with a product state at the final, or I end up with a pure state at the final time.
Well, yeah, except that that can compete against the unitaries that are generating entanglement. Right?
Yeah, that's right. Yeah. So one
I mean, it'd be the
perspective.
same thing if you just kept measuring. Well, okay, yeah.
Yeah, that's interesting. That's interesting. I don't have anything especially smart to say about it. One thing that I can mention that may be relevant here to this way of thinking is that another way to think about this transition is to imagine that my initial state is not a pure state, but some very mixed state. Like imagine my initial state is just the identity matrix. And then this, if I have no measurements, then at the final time, I also have a highly mixed state. But if I have lots of measurements, then at the final time, I'll have something that's very close to a pure state. So you can think about the same transition as like a purification transition, that if the measurements are frequent enough, then at the final time, I have something that's very close to being a pure state because it's been purified by the measurements. Whereas if I'm on the, what I call the entangling side, then I'll remain a mixed state forever.
Yeah, but what I think is interesting about the loss process is nobody has to look, right? You don't have to observe.
Yeah, that's right. That's right. Yeah, you're right. Yeah, actually, when we first came up with this, we were trying hard to find like, what are the interesting implications of this? And the only thing we could come up with at the time is that it's a sort of a phase transition in how hard it is to simulate dissipative dynamics.
Mm-hmm.
Like if you want to simulate dissipative dynamics, you can sort of follow a pure state and treat decoherence as a random measurement and average over all possible measurement outcomes. Yeah. And then this becomes a phase transition and how hard it is to do that process computationally. But okay, anyway, your suggestion is an interesting one. We should think about loss instead of measurements. And maybe indeed there could be something like a transition as a function of the loss rate. Mm-hmm. Anyway, thank you. Thank you for that suggestion. Okay, other questions? Are people feeling sufficiently rested that I can continue? I'll do the next part quickly, don't worry. Cyprian didn't give me a license to talk forever, but. All right,
sorry, I have a question.
Yeah, please.
Thank you so much for the interesting talk so far. I was wondering, like the transition so far is continuous. Is there some way to make it discontinuous?
Not that I know of.
Okay. Just a curiosity of mine. Thank you.
Yeah, so like this percolation is a continuous transition. So is there some version of it that could be discontinuous? I don't know, but there's a lot of creative work going on around this transition, and I haven't been able to follow it all, but there might be something. I don't know.
Thank you.
Okay, all right. So I mean, this is kind of the situation that there's a true transition that we don't know how to describe, and we only know how to describe it sort of by analogy with this classical percolation transition. So, our sort of hope was that maybe there's a version of this problem that's more easily solvable. And, when you're trying to solve a problem in 1 + 1D and it's too hard, you either try to go to 0 dimensions or infinite dimensions and hope the problem is easier. So what we decided to do is a kind of infinite dimensional version of the problem. And by infinite dimensional, I basically mean everyone is everyone else's nearest neighbor. So you can kind of think the version of the problem that I'm going to talk about for the next, 20 minutes maybe. You can imagine it like you have every spin, you have all the spins, and unitary operations are equally likely to connect any two. So this is, I put them around the perimeter of a circle, and I have unitaries that are these sort of bricks, and they're sort of connecting any two randomly. And I also have measurements. So now I have this process. You can call it all-to-all. We call it all-to-all problem. If I flatten out this circuit, it looks something like this. I have, these lines that are meandering from one unitary to another with no concept of spatial locality. And this is the problem that we're going to try to solve. Actually, Gollins and Hughes had a nice way of phrasing this in terms of language. They call it the bag of bits model, where you imagine just putting all of your qubits in a bag, and you only have two operations. You either pull two out of the bag and apply a unitary operation between them, or you pull one out of the bag and measure it. And again, this is a one parameter model, and the parameter is your relative rate of doing measurements versus unitaries. So I'll call that R, measurement rate R. Okay, I can't resist mentioning that there's actually a very, well, certain people who are very motivated to understand this problem. So Matthew Fisher specifically has this idea that maybe quantum entanglement can be important for the functioning of the brain. So his idea is that in the bloodstream, there's some molecules that have a very well protected nuclear spin with a decoherence time of minutes or something. And every now and then these molecules can either come together, and when they come together, they get entangled, or they can, attach to the synapse of one of the neurons in your brain. And whether they're taken into the synapse, whether they're taken into the neuron and produce a firing depends on the state of the nuclear spin for some reason. Anyway, so this is exactly like a process where sometimes your two spins come together and they interact, and sometimes they interact with a macroscopic object and either cause a firing or don't, and that's like measurement. Anyway, so the question is basically, in this kind of protocol, can you have quantum entanglement forming in a macroscopic way and persisting, or can't you? And so, okay, this isn't a reference to sort of reviewing this idea and trying to advance it. Okay, anyway, I'm not going to talk about the brain, but I just thought that was a funny motivation or an interesting motivation. Okay, so if you want to describe an all-to-all system, one of the first things you'll realize is that the concept of area law and volume law don't make sense anymore. And that's basically because there's no sense of a spatial region here. Spins are all jumbled about in a bag, and there's no sense in which anyone is anyone's neighbor's neighbor, or somewhere on the left and somewhere on the right. So one way to say it is that if you were to artificially partition it into, part A and part B, you'd find that you have volume law entanglement for kind of a trivial reason, which is just that any given spin is as equally likely to be entangled with the opposite side as with its own side. So instead, you need a different quantity, and the one that we settled on is to look at how information from the initial state persists in time. So in a heuristic sense, you can imagine there's an initial state, and it evolves into some final state by a time evolution operator. And this, because of the measurements, this is non-unitary in general. And then you can ask the question, if I know what's inside this time evolution operator, so I know the unitaries, I know the measurements and their outcomes, do I still need to know the initial state if I want to know the final state? Or is it enough to know what's inside this time evolution operator to tell exactly what the final state is and the initial state has stopped mattering? So one way to think about it schematically is that these measurements are kind of like a hole in the time evolution operator. It's a point where the state of the spin no longer depends on what came before it. And then you can ask, well, do these holes sort of connect? Do they sort of percolate across your system in some way, so that I could, by knowing the outcome of the measurements, which is kind of like the boundary conditions at all these holes, plus what's inside the operators, would that be enough to know the final time? Would I have sort of disconnected the initial time from the final time? So if you want to sort of quantify that, what you can look at is the operator entanglement entropy of the time evolution operator. And okay, I won't go into some details here. This is sort of a generalization of what I said before. And like I mentioned a moment ago in response to John's question, you can also talk about a purification of an initial mixed state. You can ask, if my initial state is some highly mixed state, it's just my density matrix is a thermal ensemble or something, at the final time, will I have something that looks like a pure state, or will I still have something that looks thermal? Okay, so let me talk first about what's the analog of the minimal cut problem. So I can sort of make a similar kind of mapping where I have my circuit, it has many broken links by measurements, and then I can ask, if I grab the spins at the final time, can I pull them apart the spins at the initial time? So in an exact sense, the mapping is that, as before, each of these unitaries is like a node in the graph, and connections in the graph, or edges, exist anytime a spin is involved in both unitaries and isn't measured in between. So for example, this red and this orange have connection because the one spin is involved in both of them and wasn't measured. But this blue and this green do not, because the one spin that would have been involved in both got measured in between. Anyway, so now I can sort of draw this graph and ask, if I grab the final time nodes and the initial time nodes, can I pull them apart? And if not, how many legs of the graph would I have to cut? And so this is a problem that you can solve, and it's not that hard. And the key thing to realize is that locally you can arrange the graph in a sort of a tree structure. So what I mean by that is to take some node that's deep in the middle of the graph somewhere, like say this purple one, and then arrange all other nodes in terms of their separation from the one you chose. So let me call this one that I chose the seed, and I sort of chose the seed randomly or arbitrarily. And then I arrange all other nodes in terms of their separation from the seed. And that's what you're seeing here. So this, say green one is 2 away, this blue one is 3. And now once you've arranged your graph into like a tree structure, now it's very easy to ask the question of, is there a connection between the initial and final time? The answer to that question is, well, are there infinite trees? Like if I do this process, what's the expectation value for the total size of the tree? And that's just a very simple, you basically just look at the expectation value for the number of, say, daughters coming off of a given node in the graph. And you'll find that so each of these nodes has 2 legs coming in and 2 legs coming out. So if I sort of arrange it in this way, there's sort of 1 coming in and 3 legs coming out. And you can just look at that expectation value and derive for yourself very easily what is the critical measurement rate. So here, as before, there's a critical measurement rate and it's 4/5. You have to work a little bit harder if you want to know the analog of the critical exponent. Like in 2D percolation, there's a critical exponent 4/3. What is the critical exponent here associated with the minimal cut? That's a little harder. There's some very clever argument here, but I won't go into it, I guess, for the interest of time. But the purpose is that the point is that you can figure out all the critical exponents for this minimal cut problem and write down exactly the corresponding minimal cut problem. That's as before, is the same S0. Okay, so you can get the same, let me not go into that, but you can calculate exactly this minimal cut business. Now, let me talk a little bit about what the 2 phases mean in this problem. So before I had area law and volume law phase, but what's the meaning of it here? And the idea is that here, when you're in the percolating phase, or what I'll call the entangling phase, where measurements are sparse, or measurements are very infrequent, what you have is that the information from the initial time, the information encoded in the initial state survives for a very long time. And particularly, it survives for a time that's exponential in the system size. So if I wait an infinite long amount of time, there's always a finite probability in a finite size system that I'll completely disconnect the initial state and the final state. So there's some probability that there will be a rare event where I measure all the spins without doing any unitary operations, and then I've disconnected the initial and the final time. But the point is that the probability of that happening becomes exponentially small in the entangling phase. Okay, let me say this a little more precisely. Heuristically, what you can imagine is take my time evolution operator and take a particular moment in time called a time slice and ask, if I wanted to sever what's above that time slice from what's below it, then how many cuts would I have to make in my graph? And that's, okay, some amount S. And then you can ask, well, what's the probability that by chance that number is 0 and it's e to the minus S? So then how many time slices do I have to look at to find one where by chance I've separated the initial and final time, and that's e to the S. So the point is that when the entanglement is S, there's a long time scale e to the S over which information from the initial time survives. That's the idea. Okay, so this is again this minimal cut problem, and we can show exactly for the 0th Renyi entropy the emergence of this exponential time scale. And let me not go into that. Okay, so the really useful thing, so this is again the classical problem, and we worked hard to solve that classical problem, but what you'd really like to get a handle on is the quantum transition. So first question is, are there indeed two critical points like before, a classical and a different entanglement critical point? And if so, can we get some better handle on the entanglement, on what I'll call the true transition? So the key insight here was to realize that the quantum circuit has a tree structure. Like if I take a spin at a given moment in time, I can separate all other spins in time in a sort of tree-like way from it. So that basically motivated us to think about, well, what does the entanglement transition look like on quantum trees? So imagine that you have, say, one spin at the root, and that spin gets entangled with 3 others, and then 3 others and 3 others, and sort of each of these nodes in this tree that I'm drawing here, vertices in the tree, corresponds to some process that has a possible projective measurement and a unitary operator. So you can describe this sequence of two things, a possible measurement plus unitary operator, as an effective one vertex that it connects one spin with three others. So just to make it a little clear, if there is a measurement, then you've basically just severed this tree and some branch of the tree is cut. But if there's not a measurement, then you entangle one with three others. And then you can ask the question of how much entanglement is there between, say, the root, the one spin here, and the leaves, which are like all others. So at most, there's log 2 entanglement because I only have one spin here. And then you can ask, basically, if I do this procedure for many, many times, if I run it for many, many generations, then is there still a finite amount of entanglement between the root and the leaves of the tree, or isn't there? And the nice thing about this tree structure is that you can write a recurrence relation for basically, say, the entanglement with the root spin and all spins at generation k, and then you can write a recursion relation that tells you, if you know that, how much entanglement you'll have with all spins at generation k plus 1. And again, I guess I won't go into that in the interest of time here. I'm already trying your patience. But I just want to say that recursion relation is something you can write down and that we were actually able to solve for it exactly. And it gives you a different critical point. So that as before, you sort of get this, the situation kind of looks like this, that you have a classical transition whose properties we can write down for where you have no, you have no mutual information between the initial and final time, because your circuit is sort of fallen apart into disconnected pieces. You have an entangling phase where you do have very long-lived information, a very long-lived persistence of information from the initial state. And then you sort of have this no man's land in between where classically your circuit is connected, but its connections are so tenuous that you do not have persistence of information. But the nice thing is that now we can derive both of these points. And from the recursion relation defined on the tree, we can actually talk about the scaling of the entanglement entropy near this critical point. And it actually turns out to be exponential, e to the minus 1 over r minus rc. So in some sense, the critical exponent looks like infinity. Okay, so I mean, we have some numerics to sort of, in addition to figuring out the tree, we have some numerics that kind of support this picture. I don't want to make a big deal about them. The numerics here turn out to be quite hard because there's no easy way of representing the state. You can't use a simple matrix product representation because there's nothing spatially local. So the numerics are, you can say that something that looks like this exponentially long time scale, but it's difficult. And all I can say is that it's consistent. But I think that theoretically our argument here is quite strong. Our argument for the existence of this transition and the critical properties. And that's relatively exciting to us to have something that looks like an exact solution for the true transition. And let me just stop there. I think Cyprian said you can go as long as 80 minutes, and that's about as much as I have to say. So the short takeaway message here is really just that in a sort of wide class of these problems where you have unitary operations plus measurements, it looks like there's a critical measurement rate that separates an entangling dynamical phase from a disentangling dynamical phase. In systems with spatial locality, that's volume law versus area law. In this system that has no space, essentially, that's persistence of information in time. And okay, here are the two references, and I'll thank you for your patience thus far. Glad to take questions.